Hi, and welcome back to Introduction to Multicast. I'm Tim McConaughey, delivering this breakout. This is part two. Part two, we're going to cover IGMP and host signaling and multicast routing with PIM. In part one, we covered basic multicast fundamentals, so if you haven't seen that, it might be better to start there. But if you've already seen it and you're catching up, let's move on. Let's talk about IGMP and host signaling, or as I like to call it, the cat to owner signaling. Now, IGMP is about raising your hand if you want multicast. So IGMP is host to router signaling. It's the signal that pulls multicast towards you. And IGMP stands for Internet Group Management Protocol. I think in the first video, I actually said it was Intergroup Messaging Protocol. Obviously, that's wrong. IGMP stands for Internet Group Management Protocol. I'm not going to go back and edit it. I think it's important that everybody realize that even the experts forget the acronyms from time to time. So within IGMP, there's two main messages. We have what's called the membership report, and that's our host to router signaling saying, I want multicast. And then we have the membership query, and that's from the multicast or the IGMP querier to the segment saying, does anyone want to receive multicast? It's like a timer. So let's look at what the IGMP report does. So the receiver will send an IGMP report out onto the wire saying that it wants to receive multicast for a particular group. And by default, a switch will just kind of flood that all across the segment to other hosts and to the routers. And so the routers will hear that and receive that report, and they'll act on it or not, as we'll see later. And then other hosts also will receive that same report, and that's important for a reason we'll see in just a minute. Now, from a query perspective, the query is more like a timer. The query comes from the multicast router, usually, or the IGMP querier would be more accurate. And the query is sent out to the wire, and it says, does anyone want to receive multicast? And it does that on a timer, on a repeating basis to make sure that they're still interested in receiving multicast traffic. And that triggers the clients that are interested in multicast to then send back a membership report. So there's two ways for a membership report to happen. One is initiated by the client itself when it wants to initially receive the multicast and it wants to let the query or the multicast router know that it wants to receive the multicast. And then it's also a triggered response to a multicast querier saying, do you still want to receive multicast? Now, there are three versions of IGMP, and they're historic. So version 1 is the oldest, 2, 3, the newest. Version 1 is deprecated now, which is to say that hopefully we're not using it on our networks anywhere. And if we are, hopefully we have a migration strategy to get away from it. But I know that in the IoT world, especially in manufacturing and stuff like that, there might still be some very old gear out there that just doesn't support version 2, version 3. But you'll see why we generally don't recommend version 1 and why it's not the default anymore here in a minute. So let's look at how the report works in IGMP version 1. So just like before, we issue the report, it goes out onto the wire, and it says, I want to receive multicast, I want to receive a certain group, and the switch will flood that, again, by default, to the routers and switches, everything on that same VLAN, and that same segment. Now, in version 1, there's a small optimization, which is called membership suppression. So if there are multiple clients attached to the same segment and they want to receive the same multicast traffic from the same groups, when a host sees a membership report from another host, it will do membership suppression. And this harkens back to the old days when multicast was first invented, when we had hubs everywhere. So there was a lot of repeaters, a lot of layer 1 repeaters in the network. And so we wanted to minimize that traffic as much as possible. So when a host would see that, it would just suppress its own report, knowing that the multicast traffic is coming and it's going to receive it. Now, the query in version 1, again, it's a multicast querier is going to send out a query onto the wire saying, does anyone want to receive multicast? And then it triggers a report from the interested receivers. Now, the non-interested receivers still receive the report, they just discard it. One of the problems with the version 1 query is that every router or every router that's running IGMP, every query, every router attached is a query, basically. So if there are 4 routers attached to the segment, every one of them will send its own query, which will require its own report to be triggered. And so that's a lot of excess traffic that we don't need. So that's kind of a failure of version 1. And then the big failure of version 1 is the lack of an ability to notify the multicast routers when we leave. So in this case, if we say the receivers are going home for the day, they turn off the application, whatever, they stop listening to the multicast feed, they're no longer interested in receiving it, the querier is still going to send a query on a 60-second timer by default. Every minute it's going to say, do you still want multicast? And it's not going to receive a report because, of course, no one's listening anymore. So, but it has to do that 3 times before it finally times out and cuts the feed. So that's 3 minutes where nobody's listening, but we're still delivering multicast to that segment. And that's kind of a huge failure of the scaling and optimization of multicast. And so that's a big reason why version 1 just isn't recommended anymore. Now, version 2 is the default now on Cisco devices, and it still is 20-something years later, maybe I forget how many years it's been. It's still the version 2 is still the default. So it's the one that doesn't show up in the config, basically. Version 2 introduces a lot of benefits and fixes for the problems that we had with version 1. So I know we're already asking, why do we need a version 3? And we'll get to that in a minute. But let's go over version 2's optimizations. So the very first thing in version 2 that is introduced is the idea of a querier election. So when the routers are booted, they'll both send queries onto the wire, and they'll hear each other's queries. And when they hear each other's queries, they will decide amongst themselves who's going to be the querier for the segment. So that'll be the only router that sends queries onto the wire until the other router that's not the querier will still listen for those queries, but it won't act on them. It'll still listen to the reports, but it won't act on them. But it just won't do anything. And it's what it's waiting for is for that first querier, the elected querier, to stop sending queries. And after a period of time where no queries are received, then it promotes itself, kind of becomes the querier. That's the failover mechanism there. They also introduced a leave message, an IGMP report that says, I'm leaving. And how it works is that the host will say, I'm done with this group or whatever. It'll send a IGMP report for a multicast group that says, I'm leaving. And what that does is it triggers a response from the M router for the segment, the multicast router, the last hop routers. For the segment, they will send a query, a specific query, which is a new kind of message in version 2. What's called a group-specific query. So when it receives that message saying, I'm leaving 239.111, that triggers the M router to immediately send a query onto the wire, but only to the group 239.111, saying, is anyone still listening? So this is an optimization that allows us not to have to flood everywhere. Only the people who are still listening to 239.111 can respond, or then receive and respond. And if there aren't any, it'll cut the feed. And if there are some, then those receivers will trigger their report and say, hey, I'm still listening to that group. And that keeps the multicast flowing. So those are 2 really huge benefits and really just kind of solve the problems that we had with version 1. So why do we need a version 3? Well, first of all, version 3 is the newest, obviously, and it's been around for I think it's over 20 years now. I need to update this slide. But it's version 2 is still the default. Version 3 introduced something that neither of the other versions have, and that's the ability for a receiver to now ask for a specific multicast source. Before, it's like a radio, right? We're tuning the radio dial to a certain multicast group, and we're receiving whatever's playing on that group. So the newest way, so in version 3, what we have is the ability to do more like an iTunes or something like that, where we can say, I want to listen to a specific source. I want to listen to Foo Fighters or whatever specific feed that it's looking for. And that didn't exist in version 1 or version 2. But in version 3, we can say, I want to listen to this group, but only if this person is playing. I want to listen to this source that's playing on this group. And what that allows us to do also is to scale our multicast groups, because the source and the group are a pair. So we can actually overlap our multicast group without overlapping our multicast feeds, because we can select different sources, even using the same multicast group. We're asking for specific sources, and that actually is a different flow. So there are some weaknesses with this also, but the main thing is that it allows us to scale our groups up. And then lastly, we'll talk about IGMP snooping. And IGMP snooping is an optimization. It's not so much a security thing like we would see with DHCP snooping, but it's more of an optimization insofar as the switch will be listening for these multicast messages and then learning on which ports certain devices are performing certain roles. So as an example, when the routers come onto the segment and send an IGMP query, the switch is going to learn, okay, so on these ports and in this VLAN, this is the device that's going to be the querier for the segment, and so it's going to optimize the multicast flow. If it doesn't know any of this information, by the way, by default, the switch just floods multicast traffic. So if there's no optimization at all, the switch will read the multicast MAC address and just kind of flood it out. So this is an optimization for scaling and for optimizing the traffic flows. So in this case, when the routers come onto the segment and send a PIM message, which is what we'll be learning about next with multicast routing, the switch also learns that information and says, oh, I have 2 multicast routers in this case attached to this segment, and this is the port on which those multicast routers exist. And then, of course, from the receiver's perspective, the switch will learn on which ports for which groups receivers exist that want certain group multicast traffic. And notice also that we learn the version of the IGMP message that we send out. Now let's talk about multicast routing. Before we talk about how multicast routing works, we need to review how the unicast control plane works and how unicast routing works. So given this segment here, we have several routers connected to several networks, and through whatever routing protocol they like, they're going to advertise the reachability to these networks to the other routers. So in this case, let's say we're using EIGRP. So the top router, or the first hop router, will advertise that it's connected to 10.3.12.0, and it's going to advertise reachability to the other routers. And so they know that if they want to send a packet to that network, that they're going to forward it, out of certain interfaces. And the same is true in reverse, right? The last hop router with the connected network for the receivers is going to advertise reachability to the top server segment. And when it's all said and done and the dust settles, the routing protocol will have helped figure out the best path between the receiver segment and the server segment, so that when a unicast packet is sent, the destination would be, say, 10.3.12.17 or something that the server is using, and it's sent from the receiver. And again, we're not talking multicast now. This would be just if we're interacting with the server. That packet will flow along the best path based on the destination, which is the server. Every router along the way is going to look at its RIB and decide what is the best path to reach this network and forward the packet that way. And when the receiver sends the return traffic, it's going to do the same thing, saying the destination is 10.1.200.6 or something like this, and it's going to forward the packet, and every router along the way is going to consult its RIB and find the best path and over which interface it should forward the packet with the destination of 10.1.200.6. Now, before we go any further with multicast routing, this is very important. Multicast routing itself is not enabled by default on Cisco devices. So even though we could configure PIM, Protocol Independent Multicast, even though we can configure PIM and get neighbors, the actual data plane multicast will not flow until we turn on the multicast routing for the device. So we enable that at the global level, with IP multicast routing, and distributed is, of course, if we have distributed cards. So now let's talk multicast routing. PIM, Protocol Independent Multicast, is a link local protocol, which means it's one hop. It's between two routers, and it works on that hop-by-hop basis. And it relies upon the unicast routing decisions to build that loop-free multicast river or canal. When we talk about how does the receiver receive multicast from the source, it's that loop-free multicast river that gets built from the receiver up to the source, and then the traffic flows backwards along that path. We're using the unicast rib to build that loop-free topology because PIM is not concerned with best path. PIM is concerned with tracking multicast traffic and sources and groups and receivers. Now there's three modes of PIM. So PIM dense mode is kind of a legacy mode. We really shouldn't be using it. PIM dense mode multicast is, if we say that multicast is kind of like a river, then PIM dense mode is the idea that we're going to flood the banks every, I think it's 3 minutes. All multicast traffic will be flooded everywhere, and then it would be up to the last hop routers, or just any router that didn't want to receive that multicast traffic. They'd have to throw up dams, basically. They'd have to send what are called PIM prune messages saying, I don't want the multicast. So it would flood the banks, it would show up, it would go everywhere, and then it would be up to those routers to basically build dams backwards towards the source saying, hey, actually, we don't need multicast, please stop sending it. And that's a process that's repeated every 3 minutes. So it's a bad process. We don't want to use it because we can cause loops, we can spike network traffic every 3 minutes, and of course it's not scalable, it's not optimized. Now PIM sparse mode is the current implementation, that's what we're using, and that's when we talk about multicast 99.9% of the time, this is what we're talking about. We're talking about sparse mode multicast, which operates on a pull method, which is why we need things like the IGMP report and things like that, so that the receivers can actually signal for multicast and ask to have it delivered so that we can build that loop-free, optimized multicast river back towards the source. Now there is a third one. It's called PIM sparse dense mode. It's really deprecated now. We're not really using it. We're not pushing it. We're not suggesting people use it. The idea was that we would run most multicast groups in sparse mode. We would run the groups that we needed to in dense mode, and then we'd get the best of both worlds. But really, we ended up getting kind of the worst of both worlds. And there's really only one reason or one solution that ever requires sparse dense mode, and it has its own workaround now. So sparse dense mode is no longer needed. And we'll talk about that solution later when we get to any source multicast. But just understand that sparse dense mode is the idea that we're kind of doing both, and it's not required anymore. So what are the requirements for protocol independent multicast? Well, first of all, we can only forward multicast traffic in the data plane on interfaces that have PIM enabled via the IP PIM, whichever mode that we're using command. We have to enable PIM towards the source because PIM is basically how we forward multicast. It's also how we listen for multicast. So if a router, first hop router, is connected to a segment with a source, but PIM is not enabled towards that segment, the multicast source can be sending packets to the multicast group all day, and the router's just not listening, and it's not going to pick it up, and it's not going to follow the multicast process. Now let's talk about multicast routing, and let's talk about reverse path forwarding. Reverse path forwarding is how we make sure that we have a loop-free traffic delivery. Remember that PIM does not use its own best path algorithm. PIM is relying on the unicast table to tell us what is the best path, and we're going to use that best path decision to set up that multicast river. So When a source sends multicast data packets to a multicast router, the interface on which that multicast traffic comes into the router is checked against the source of the packet. So the router looks at the packet, says, what is the source of the packet? Now remember, the destination is going to be a multicast group, so that's not going to be any good for this process. We have to say, what is the source of the packet? The source of the packet would be some network, some device, some host. And what the router will do is compare that source IP to its RIB and say, what interface would I use to forward a packet to that source? It says, what interface would I use? If the interface that I use to send it to that source is the same interface on which I receive the packet, there's no loop, because that's the path I would take. So the unicast RIB says that's my best path. That's the interface on which I got the packet for that source. So we must not have any kind of loop. Everything's good. Now, if something happens where, say, there's some routing instability or a link is lost and a best path changes, if something happens where if the best path to the source of that packet is a different interface than the interface on which it actually received that multicast packet, there's no way to guarantee this is a loop-free. This is not a multicast routing loop. And so it's going to discard that packet. And so it's important that we understand our unicast routing table and the best path decisions of our unicast routing table in order to understand the multicast traffic flow. And we'll see that a little bit later. I'll show you in a demo at the CLI level what that looks like. Now, PIM is primarily responsible for tracking the incoming interface and the outgoing interface list for multicast group. Now, the incoming interface is based on what we just talked about. The incoming interface is the interface on which we expect to receive a multicast packet based on the source. So when a receiver sends that IGMP report and it's turned into a PIM join is forwarded towards the source. If we know who the source is, the PIM join is forwarded towards the source based on the unicast best path to the source. So in this diagram, those green arrows are, say that was a PIM join that was forwarded by the multicast router towards the source of the multicast traffic. And each router along the way looks at its RIB and says, what is the source of the multicast traffic? Okay, this is the interface on which I would forward that packet. And so it forwards that PIM join up the river, digging that canal towards the source. And that becomes the incoming interface, the interface on which that router expects to receive the multicast traffic. So per router, per multicast group, there is only one incoming interface allowed. And that should make sense because we have to make a best path decision. We have to choose an interface on which we're going to forward a PIM join. Now, there's no ECMP or equal cost multipath. There's no multiple paths in multicast. With multicast, we have to pick a best path because we don't have a full view of the routing table. We don't track our best path with PIM. So PIM has to pick one best path. If there are two best paths, then PIM will pick one based on the IP of the PIM neighbor. I believe it's the highest IP of the PIM neighbor. Now that's different than the outgoing interface list. The outgoing interface list could be basically any interface that isn't the incoming interface. The incoming interface and the outgoing interface can't be the same interface. That's a split horizon type of setup that's not supported. So any interface on which a router receives a PIM join becomes part of the outgoing interface list. Now let's take a closer look at how PIM joins happen. At first, the client will send an IGMP report, which will go over the segment and go to any multicast routers that are on the segment. Now, the multicast routers will not all send PIM joins up towards the source. There's an election that happens between any of the last hop routers attached to the segment to determine who's going to be the M router for the segment. There's a priority that can be configured, and otherwise it uses the, I believe, lowest IP address of the PIM neighbor for the segment, and that router will be the one that will then forward PIM joins for that segment, unless it goes down, in which case the other one will take over. In this case, LHRB is our M router for the segment. It's going to convert the IGMP report into a PIM join and then look at the IGMP report to ask for which group and which source the request is coming in. So in this case, the group could be, say, 232.0.0.100, and the source would be 10.3.12.2. Because that's the source, LHRB will consult its routing table and determine over which interface it would forward a packet to that IP address. And that will be the interface over which it forwards the PIM join. Again, digging that canal or that river up towards the source. And when we get to the source, we'll open the floodgates, and then based on those PIM joins, that traffic will flow backwards towards the receiver. Let's take a look at the multicast routing table here on LHRB. Notice that the outgoing interface list includes gigabit 02. Now that is the interface facing towards the segment where it received the IGMP report. So it added that interface to the OIL, or the outgoing interface list, based on that request. Notice also that we're asking for an S, G pair in this case, 10.3.12.2 being the source, 232.0.0.100 being the group. Also notice that the incoming interface is marked as gig01. The incoming interface is the interface on which we would forward a packet towards that source, 10.3.12.2. So it forwarded the PIM join out of that interface up to the next router and marked that interface as the incoming interface on the interface in which it receives or expects to receive the multicast traffic. Let's look at the next router. The next router receives a PIM join on gig02 and therefore adds it to the outgoing interface list for that source group pair, and consults its RIB, determines what interface it should forward that packet out of to reach that source, forwards that PIM join based on that RIB lookup, and then it's going to hit the first hop router. At that point, the floodgates should be open and we can actually deliver the multicast traffic. So let's look at the delivery. So once that canal has been built, that trench has been dug, and the floodgate is opened on the first hop router to allow the multicast traffic to flow, it's going to flow backwards along the path of the PIM joins that it received, back towards the receiver. So at the top, you can take a look here at the first hop router mroute table. The incoming interface is the interface facing the segment on which the source resides. And the outgoing interface, again, will be the interface on which it received the PIM join and added it to the OIL. So now, because we have an incoming interface, an outgoing interface, and we're attached to the source, that floodgate is open and that multicast routing will now take place. And multicast traffic will follow that OIL, or that outgoing interface list, hop by hop on the routers back to the receiver. So what happened to LHRA? It received an IGMP report, but as we know, it was not elected the M router for the segment. We can see that it received the report, it's in the mroute table, and LHRA even figured out what interface it would use to forward that PIM join towards the server. But it didn't actually send the PIM join, and also notice that the outgoing interface list is null. It's null because, again, it wasn't elected the M router for the segment, so it never added the interface to the outgoing interface list. And this is the loop prevention mechanism. This and RPF, reverse path forwarding check, are the loop prevention mechanisms for multicast. Now let's jump over to the demo and take a live look at some of this stuff that we've learned with the IGMP snooping and the PIM multicast routing. So to jog our memory a little bit, we have receiver 1, which is a PC, receiver 2, PC. We have our L2 access switch, which is going to be performing our IGMP snooping. And we have our two last hop routers attached to the segment, last hop router A and B. So let's get into them. We'll see what IGMP snooping looks like. We'll see how the last hop routers handle IGMP and get some traffic flowing. So here we are on receiver 1. Now, I don't believe I have any multicast running at this time. And, well, I know I don't have any multicast running. I don't believe I've sent any IGMP reports at this time. And no, I haven't. So this is kind of a pristine setup where we have no groups, no reports have come across the switch, and our last hop router A and B are also pristine. They don't have any IGMP reports sitting there. If we look at the rest of the network, of course, we've got the same thing going on. We can log into the first hop router. I haven't sent any multicast traffic, so let's just take a look at the mroute table, which is our multicast routing table, and you'll see that, and you can ignore this for now. This is a specific multicast group for a solution called AutoRP that's on by default with Cisco devices. We'll cover this in the next part when we talk about any source multicasts and rendezvous points. But you can see that we have no traffic flowing at this point, and we have no request for multicast traffic at this point. It's kind of like I said, a pristine setup. We've got nothing going on. So go back to the receiver, and let's go ahead and send an IGMP report. And because in this demo, the receiver is really just a router with a connected interface, we'll just go to the interface and issue a static IGMP join. Let's do that now. We'll join, say, group 239.1.1.1. And that should be sufficient to issue the IGMP report onto the segment. Should be learned by the switch at this point. And it is. You can see that we have an IGMP report for that group. It was a version 2 report, which again is the default on Cisco devices. And you can see that we learned it on port gig 03. Now, what does it do with the report? It's going to send it up to the multicast routers on the segment. So if we look here, we should be able to see the M routers for the segment. Oh, I did that wrong. Snooping M router. Now in this case, we only see one. That's going to change here in a minute. Something probably timed out. But there are 2 multicast routers on the segment. As we saw earlier, we're going to use LHRB as our multicast router. In fact, we can check that right now. So let's do that. IGMP interface gig 02, which is the interface that's connected to the switch. And this is a very helpful command. It shows us everything we want to know about the interface, what kind of IGMP stuff it's doing, basically. So if we skip down to the bottom, we can see that the IGMP querying router is 10.1.200.2. Now that querier, remember, is the one that's going to, every 60 seconds, send that IGMP query onto the wire saying who wants multicast. Now, that isn't this system. That's actually LHRA was elected as the IGMP querier for this system. Or for this segment, rather. Now, if you look above it, though, this is the multicast designated router. So the multicast DR or M router for the segment is 10.1.200.3. Says it's this system. So when an IGMP report comes in and we're going to convert it to a PIM join and start that process of pulling the multicast traffic towards us, this is the router that's going to actually forward that PIM join. The other one's just going to sit there. So now that we've seen that, let's see if we have any IGMP reports reported. So show IP IGMP groups. And you can see that we've learned on gig 02, again, the interface down towards the switch, we've learned a report for 239.1.1.1, and the reporter, which is 10.1.200.6, which is our receiver 1. So at this point, we should have converted this to a PIM join in order to start that router-to-router signaling and pulling in the multicast. Thanks for watching part 2. I hope you learned something about IGMP and basic multicast routing. In the next part, we'll cover any source multicast and the rendezvous point that goes along with it. We'll also spend a lot more time digging into the CLI and understanding how multicast traffic flows. Hope to see you in part 3.